course, thank you. Hello, everyone. My name is Biajani Gonzalez. I'm an NCASM fellow from the University of Puerto Rico, Midwest. And today I'll be talking about the development of a low-cost sensor system for estimating the diffusive ventilation coefficients in coastal waters. So before we get any further, I want to figure out how the structure of this presentation is going to be. First, I'm going to be discussing the background and relevance of this research. Why are we doing this? What's the context? Later, I'm going to be talking about the methods and materials, the methods we took to gather this data. And then finally, we'll be talking about conclusions. We'll analyze the data and conclusion. So before we go any further, we must ask ourselves, why exactly do we measure the diffusive ventilation coefficient? Well, in actuality, it serves to be one of the best optical parameters to assess water quality conditions worldwide. Furthermore, it also serves as a broad indicator for the availability of photosynthesis, that which many aquatic organisms rely on. And if we already know KD, we can also calculate the incident downwelling irradiance, also denoted as ED, at depth Z using the following formula. And as you guys can see here, this is a graph pretty much representing like the behavior of downwelling irradiance. As you can see, the deeper we go, the lower the downwelling irradiance will be, showing an exponential decrease. All right, so now that I get kind of like a brief background overview, we must ask ourselves, so like what's the deal, right? Why are we doing this? Well, access to low-cost light sensor systems can provide reliable measurements of KD, while also increasing the number of water quality sampling and number worldwide. However, the problem is that there's very low access to light instrumentation remains relatively low on the market, where higher end sensors still remain as the standard. So then we must ask ourselves, what low-cost alternatives could be proposed for more accessible underwater light instrumentation? So with that said, our goal is to emphasize a do-it-yourself low-cost sensor deployment model utilizing only Cobo pendant loggers, those which are more low cost and compared to higher-end sensors. So I'm going to give a brief overview of the objectives. As mentioned prior, we want to develop a low-cost, easy-to-use device for measuring water quality conditions. In this case, we will be measuring KD using a pair of Cobo pendant loggers. Now, once we have this, we will compare data, lumens data, with Cobo with a more higher-end sensor called the solar light. And once we do so, we download the data via the Bluetooth application, and we will calibrate the Cobo data using linear regression to solar light data. By doing so, we will also be calculating the KD. And finally, we will be comparing this data set with the other data set to see whether or not the Cobo sensors are reliable. So this is just a brief methodology of the previous objectives. Like I said prior, we'll be collecting Cobo and solar light data across a variety of environments within Puerto Rico. I will mention further on which environments we'll be looking at. We will be calculating the KD by both sensors. We will then be pre-processing and comparisons of the data, discarding the data that is not worthy, and pretty much making those connections as to what attributes to errors could be applied. And then, finally, that's the error analysis. So for this experiment, we pretty much focused on two deployment models. Now, the proposed deployment model will be utilizing two Cobo pendant loggers, two of which are separated at a fixed distance of 0.5 meters. This model is light, compact, and easy to transport. Meanwhile, on the left, we have the solar light with Cobo's deployment model. This model, however, will only be utilized for comparison system data. So now we come to the sampling steps. This, I'll be honest, is like the most boring part. But so basically at each assigned station, we pretty much had the solar and Cobo instruments acquiring simultaneous data for approximately 6 minutes at each step. We could go further more than 6 minutes, let's say 10 minutes ideally, but we pretty much found that the minimum time to obtain an accurate approximation was 6 minutes. Once we did so, we then downloaded that data via the Bluetooth application, in which we obtained it from a CSV file. We then applied the following equation in Excel in order to calculate the downwelling irradiance. As you can see here, the median lumens of Phobos is the median value of Phobos in each depth. The 0.0185 is the conversion factor of lumen/meter squared to lumen/feet squared. which that's also another thing. And the Bluetooth application by default, this data as unit/meter squared, and we don't want that. In order to calculate the downlink radius, we need to have it in feet squared. Then finally, we multiply it by 0.093, that which is the conversion factor to derive photosynthetic photon flux density. So once we had that data, we analyzed, we applied the equation, we then could find the diffuse attenuation coefficient. And to find it, we use the following formula. As you can see here, the C variables are associated with the depths, where C1 is the top sensor depth, that which is associated to the top Cobo sensor logger, while C2 is the bottom sensor depth. And as mentioned before, the downlink radius is associated to ED. So we're pretty much applying the logarithmic value of ED of the top sensor divided by the ED of the bottom sensor. All right, so the sampling station. So for this research, we considered a wide range of environments throughout Puerto Rico, but the main worthy ones were 3 of them. We had oceanic areas, which you can see in the top right. We had the coastal turbid areas, which you can see in the top left. And finally, we have the lakes and estuaries in the bottom. Now, it's important to note that each area will have different optical properties, that which will influence the KD results. So now that we gave a brief background overview of the methods, how exactly we went about this research, here we can see a preliminary data comparison of Cobo sensors and solar light bar sensors. So as you can see, the Cobo sensors are associated with the blue color, while the solar light sensors are associated with the orange color. Now, we can see that there are slight differences in the data, but they are close, if not exact. However, we can't only base ourselves on this to further confirm the reliability. We then took this data and applied linear regression, in which the sampling, at this moment, the sampling here was n equals 10. And by doing so, we obtained a high R-squared value of 0.9269. Now, again, considering that the sampling number was 10, this is a very promising outcome. Furthermore, showing the reliability of these sensors. So once we had that data set, once we compared the reliability, whether, are they worthwhile using, we then decided to, okay, well, let's expand that data set, but only focusing exclusively upon Cobo sensors. As you can see here, these first values are associated to oceanic waters, where the average KD scored it to be 0.145. Now, it is important to note that these waters are allotropic, very light and blue in color. Furthermore, due to the lack of nutrients, the light penetration depth will be far deeper. And second to that, we had the coastal waters, which they exported an average KD of 0.502. Now, this is pretty much like the medium of the environments observed. And it's important to note that these waters had more turbidity compared to the oceanic waters. There was more turbidity, wave action, and suspension of bottom sedimentation. So as you can see from the pattern here, we can definitely say that the more organic and inorganic suspended matter in the water column, the higher the KD will be. And a higher KD will result in a lower penetration depth for light. And then finally, we have the lakes and estuaries. These quoted an average KD of 0.67, which just makes sense considering that these waters tend to be very much more turbid compared to the coastal waters. That can be associated to bottom sedimentation, color dissolved organic matter, chlorophyll, basically organic and inorganic matter. Concluding this research, we pretty much said that though Cobo sensors are reliable in the long term, they are more sensitive to external factors when compared to solar light bar sensors. These factors are mainly attributed to external factors out of our control. This can be cloud interference, weather, wave action, and the boat position. So we must always anticipate and be prepared for the worst. This means whether you're checking the weather, assuming the best boat position, checking for any clouds, etc. And I say this because that's a big problem we confronted in our research. A lot of the time when we were measuring these instruments, let's say we're measuring the Cobo logger, and we had an average lumens, because at the time we were measuring lumens, we had an average lumens of 6,000 to 700,000. But the smallest interference of one cloud would plummet that value down to 2,000 lumens, which will heavily influence the data. So again, we must always anticipate and be prepared for the worst. So on the long term, what does this mean? Well, we can definitely say that Cobo loggers can provide a reliable KV value, that which is on par with more higher-end sensors, thus making it a promising low-cost sensor deployment model. This has the potential of increasing the number of sampling frequency and quantity of water turbidity worldwide. This can include non-governmental organizations, watchdog organizations, marine science centers, environmental consultants, but most importantly, our main target of this research, which are citizen scientists. And yeah, I like to give a shout out to my family and friends and my mentors. I like to especially give a shout out for NCASM for the funding. And Alba Guzman, she's right there in the back. Thank you for the field data collection. And Diego Santiago, he's not here, but we're pretty much working on a software development to automate this data. And yeah, this was all made possible by the U.S. Department of Commerce, NOAA, the EPP. Thank you.
Any questions?
Did your solar AR when you're comparing the Cobo to, did it measure direct irradiance and also angular specific irradiance, or was it just?
From my knowledge, it was only direct radiance. Okay. Yeah.
Thank you.
Of course.
So you're saying that the Cobo is more sensitive to interference, which might make it a little bit harder to use.
Yeah.
Does it make it still, since it's so much cheaper than the solar, is it still cost effective to make all those interference?
Oh yeah, it is heavily cost effective. Thing is that the solar light bar sensor is approximately $600, while each Cobo sensor costs $75. So this model in total is like around $150, and there's the difference in that is $500. So right, we have these external factors that do influence the data greatly. And again, they're more sensitive due to the light focusing effect of the sensor. But as long as we take that into consideration and assume the best, factors in hand, we can gain the best out of it. Thank you.
So that software is basically for ease of use in that sense. It's not going to be analyzing any extra data.
Yeah, pretty much. So to expand on that, we're pretty much planning on automating this process. But furthermore, we eventually, well, I don't want to say we're going to do it. This is like an idea, right? But we want to see if we can create an application so that anyone worldwide, let's say you're a commercial scuba diver, right? You have these Cobo pendant loggers in hand and you're going to go dive. Well, while you do that, you want to leave that, measuring lumens at the bottom, at the top surface. So the goal is to eventually create an application where we can upload these findings and anyone else, thus increasing the sampling frequency and quantity of these measurements. Thank you.